So welcome everyone to the fourth meeting of the AI Reading Group by Women in AI and Robotics. My name is Cleo Norris, and we're really excited to create a space for direct dialogue between researchers and the community to allow for deeper engagement with emerging research. So with that, I'm excited to introduce our speakers. Yudi Zhang is a second-year Ph.D. student at Eindhoven University of Technology, and she also works closely with Professor Yali. Prior to joining the university, she obtained her bachelor and master's degrees from Shandong University. Yudi's current research interests lie in causal reinforcement learning, multi-agent reinforcement learning, large language models, and embodied AI. Dr. Yali is a senior lecturer in AI at King's College London and a Turing Fellow at the Alan Turing Institute. She leads the Cooperative AI Lab. Her research aims to enable machines to exhibit cooperative and safe behavior in intelligent decision-making tasks. Her work focuses on reinforcement learning and multi-agent cooperation with topics such as generalization, zero-shot coordination, evaluation of human AI players, and social agency, for example, human-involved learning, safety, and ethics. And they will be presenting the paper, Interpretable Reward Redistribution in Reinforcement Learning, a Causal Approach. So with that, I'm excited to invite the speakers to share their screens. I'll spotlight.
Thank you. Is that okay?
That's perfect.
Okay. Then let's start. Thank you. Hello, everyone. I'm Yudi Zhang from Eindhoven University of Technology. It's a pleasure for me to be here today. I will share our NERPS paper titled Interpretable Reward Redistribution in Reinforcement Learning, a Causal Approach. This work, which we call it GRD, Generative Return Decomposition, addresses one of the fundamental challenges in reinforcement learning, termed delay rewards. To solve delay rewards, our research explores how causality can play a significant role in making reward redistribution more interpretable and effective. Today, I will introduce our work from 4 sections that address the problem delay reward, the proposed causal reformulation, and our methodology and the experimental results, including the visualization of the NERD code structure to show the interpretability of our method. So, for the first part, the delay reward. Delay reward is a well-known challenge in reinforcement learning, often leading to instability of the policy learning process. For example, let's consider such a game where the goal is to find the treasure. The navigator only receives a positive reward upon successfully finding the treasure. The absence of immediate feedback during the journey makes the policy optimization unstable and inefficient. To address this, the typical method, reward redistribution, assigns proxy rewards to clarify the contribution of each state action pair in each time steps, providing immediate feedback and stabilizing the optimization process. So in our work, we emphasize that it is equally important not only to compute these contributions, but also to explain the reason behind them. So that is our motivation. By modeling the generation of Markov in rewards, we create a new framework for interpretable reward redistribution, which further enhances the policy learning by offering insights into decision making. So here I introduce the causal reformulation of reward redistribution. Causality is really a natural tool to model the relationship between causes and outcomes. So in our work, we want to investigate the cause of Markovian reward, that is, which part of the state action pair will cause the Markov reward. Here, Markov reward serves as the goal of reward redistribution. That is, the recovered or estimated Markov reward would be the proxy reward, which used to replace the episodic reward for further policy learning. Here, we provide a graphical example in the slides to illustrate the causal model in the proposed reward redistribution. Specifically, instead of the Markov rewards RT, here the blue note, we can only observe the delay rewards. Usually, reward redistribution follows the assumption of return equivalence to keep the NARD policies before and after the reward redistribution the same. So we can assume that long-term returns, the green note, are observable because the episodic reward is observable. In the example, as shown in the picture, the state vector has 3 dimensions, and the action vector has 2, with the solid lines indicating the causal relationships. For example, consider the first dimension of the state at the given time step t plus 1, which is influenced by its causal parents, the state's first dimension and the action's first dimension from the time step t. These connections from one time step to the next time step define what we commonly refer to the dynamics function. And similarly, we also model the causes of the Markov rewards. That's some part of the state vector, and some of the state components and some of the action components will impact the Markov reward. So we can know what's the cause of the proxy reward. That's why we call our method is interpretability. Has interpretability. To keep the optimal policy environment just mentioned before, we follow the return equivalence assumption to calculate the long-term return as the discounted sum of observed delayed rewards. We now can organize the previously discussed causal graph by mathematics, capturing the dynamics function f, which takes as input the causal structure from state and action to next state, and the state, the action, the noise, and also the Markov reward function, which takes as input the causal structure between state to reward, the causal structure between action to reward, and the state, action, and noise to model the generation of Markov reward, and also the generation of long-term return, which follows the return equivalence. So, the causal structure in the previous graphical example now is captured by the four binary masks. Specifically, the CS2R with the shape of S and the C action to reward with the shape of A, indicating if a specific dimension of state and action influence the Markov reward RT, respectively, and also the code structure from state to state denote the causal edges between the state and action to the next state. We further provide the identifiability results as here, supporting the recovery of the unknown functions f, g, and the causal structures, the 4C, to from the data. So if you are interested with this, can refer to our appendix in the paper for more details. So how we estimate the generator model, just the mathematics functions. We minimize the mean square error between the discounted sum of delay rewards and the predicted Markov rewards. Here, R is the long-term return, and RT hat is the predicted Markov rewards. So we minimize the MSE loss. Also, we maximize the likelihood of the next step given the current state, action, and the causal structures. We further use the regularizer to force the causal structure become sparse as possible to avoid some trivial solutions. And the total loss is the sum of the three loss terms. So after optimize the generator model, how we exploit it. So give the parameterized generator model. First, we replace the observed delay rewards with predictive Markov rewards to supervise the policy optimization. That is a common practice in the previous work. And second, we replace the observed state with the compactive representation, which is a minimal sufficient subset of the state dimensions for policy learning. We say a state component SIT belongs to the compact representation if it directly causes the reward. Like S to T here. And also, if it causes alien dimension of the next state, which further influence the reward, like S3T here. So it belongs to the compact representation. After get the compact representation, we will take it as the input for policy, and the policy learning will be guided by the redistributed reward. Let's see some experimental results in the episodic Majorco. What is episodic Majorco? In Majorco environment, usually the agent can observe a dense reward, that is RT. But in episodic Majorco, the agent can only observe a delay reward, an episodic reward, that is discounted sum of RT. We denote it OT if T equal capital T. That is the end of this episode. And otherwise, the agent can only observe a reward that is 0. So such a delay reward will make the policy learning very unstable. As shown in the slides, our method GRD, the red line, outperforms the ablation version GRD without CR. That is, we remove the compact representation and make the policy input as and take as input all the state component. So we can see our method GRD, the proposed compact representation indeed improves the policy learning. And for the other lens is our best lens. So our method GRD also outcomes all the best lens. So we mentioned before our motivation is the interpretability. We achieve this by the nerd causal structure. So let's see how is the nerd causal structure. Take ant as example. This is one of the scenario in the Majorco. uh, it has two characters. That is the 28 to 111 dimensions in the state are not used in this environment, and also it achieve low cost control. That means all dimensions of the action components cause the Markov rewards, the proxy rewards. That is what we know before. We know for ground truth. So let's see how the numerical structure in this scenario. First, there is a few edges connected to the no-used states, like here. Since they do not influence the reward, and all the dimensions in the action connect to the rewards. Here, it's blue in blue, so means the causal edge exists. And the above indicates our numerical structure are corresponding to the ground truth. So the edges relate to no used state do not exist. So they are in yellow. And you can see here is some not redundant edges, but they are not in compact representation. That means the policy won't take it as input. Because these edges, although this state component impact next state, but the next state Sj t plus 1, it won't impact the Markov reward. So we didn't consider it in compact representation. And the edges from all dimensions of action to reward exist. And we also visualize the redistributed rewards. As shown in the picture, the blue solid lines, that is the ground truth Markov rewards. That is the redistributed rewards. And the red lines, that is the ground truth. So you can see the visualization demonstrates the accuracy of our method to recover the Markov rewards. So that's all. Thanks for your attention. So maybe let's enter the QA session.
Absolutely. Thank you so much, Yudi. That was really interesting. I'll invite our audiences both on Zoom and Hugging Face to just put your questions in the chat or raise your hand. Yudi, I'll give you a second. I won't fire them at you right away. Let's see. They've gotten. Okay. So we have one question from Hugging Face, and that is, does this work outside of a limited number of actions and states? Judging from the example, it seems like it can do continuous states. Also, Yudi, if you're still having technical difficulties, we don't have to jump in right now.
Sorry, I'm not sure if I still sharing my screen.
It is, but no rush.
Okay. But can you see the slides?
No, just your desktop.
Okay. Maybe, sorry. For the question,
Oh yeah.
Indeed, in this work, we assume that we have limited state component and also a limited action component. But we also work on some extension of this work, so we can extend this work also to address like vision-based RL. That is so. Maybe in such a setting, we cannot access to the state component, and yeah. And also there are many technologies in in like represent learning, causal learning to estimate uh, the state component. Yeah. So is this?
Yeah, if anyone has follow-ups, feel free to send them in, but that was very helpful. And now a question from our Zoom audience. Instead of MuJoCo, can we apply your interpretable reward redistribution algorithm and methods with a custom OpenAI gym based on, I'm not sure, that ALE, ProcGen, and or petting zoo environments?
Uh, um, I think it's also okay because we don't assume that our method only applied in some in such a environment in Majoko, and so I'm not sure what's the characteristic for those environment. Uh, yeah, that to make the audience think it's not suitable to apply, but I assume that maybe it's because um maybe they are maybe we cannot access to the full state. I think it's similar to the last question. In such of in such environments, that we cannot access to the state, the full state. We can have some technique to estimate the state component. So upon the estimated state component, we can apply our method.
Okay, wonderful. And I think there was a bit of a quote from a paper as a follow-up, but I think that really answered the question. And you can let us know in the chat if you have another question on that. So personally, I was wondering, kind of zooming out to actually using GRD, what kind of computational challenges arise when integrating causal modeling into reinforcement learning algorithms, and how does the GRD framework overcome these?
Oh, it's really a good question. Uh, I think uh, I think the in practice, the challenge I encountered, using the reinforcement learning, the collected sample are not balanced, like because uh, during the exploration we may only use uh, one policy or some random policy to explore the state space, but usually we cannot explore the state space. We cannot fully explore the state space. So, I mute.
Oh, no, I
Okay.
can hear you.
Oh, okay. Okay. So, usually we cannot fully explore the state space, so that we cannot estimate the causal structure very um we cannot estimate the ground truth causal structure. But it's also very easy to solve. Like we can collect, we can start to do the policy optimization after we uh, estimate the causal structure. We optimize the causal structure for a period of time. Yeah. So in practice,
Mhm. Thank you. Um, yeah, that's really interesting to me, especially as someone kind of like in industry watching people try to implement things. But I think sometimes research doesn't necessarily like, need to consider these things. So, but that's really interesting. And feel free to keep sending in questions from our two audiences. But I'll continue us on with our discussion. So how could the GRD framework improve the transparency of RL algorithms and systems in critical applications like autonomous driving or personalized medicine? Because I noticed kind of when in your discussion in the paper, it really spoke to helping to make AI systems more trustworthy for humans.
Yeah, that's the motivation of our work. We think interpretability, the transparent of the AI system is really important for its implementation and application. Um, so I think because our work is to narrow the code structure and use the code structure to enhance the policy learning. So I think if we can know the code structure, we can know what component of state and action can impact the reward. So we can know why the AI system or the agent choose to act like this. Maybe we can know which part of the state can increase the reward. So that would be helpful for human to understand why the agents perform like this. Yeah. So
Absolutely.
I think it's really interesting question regarding our motivation.
I totally agree, and I've seen a little bit in the literature of reinforcement learning being used more frequently in personalized medicine, for example, where it's like again, it's in healthcare. It's really important to get things right and to understand why the AI is making the decisions it does.
Yeah.
So yeah, that's very cool. Um, so. This is very extremely related, but by improving interpretability in RL, could frameworks like GRD help address regulatory or ethical concerns about the quote unquote black box nature of AI in safety critical domains?
Yeah.
Mhm. Um, yeah, I think legislation is a whole other kind of topic to cover, and sometimes it's very interdisciplinary, but yeah, I think that really goes toward it. Um, okay, so moving on. Um, this is kind of more into that graph structure we saw from the paper from the causal graph. So the GRD framework relies on well-specified causal graphs to perform reward redistribution. So in scenarios where the causal structure is partially incorrect or incomplete, how does this impact the reliability of the redistributed rewards? And what mechanisms could be incorporated to GRD to make such imperfections more robust? That's kind of a big question, so it's okay to break it down.
Uh, it's um it talks about if I understand
Yeah, yeah.
correctly, it's talking about if the node causal structure is wrong or incomplete.
Yeah, and more incomplete.
How
I feel like, yeah, if that's
uh,
more common.
Yeah, yeah. I think it's really um it's indeed existed a problem in the framework and in during the policy learning. Just like I mentioned before, um yeah, uh we uh we can optimize the policy after we estimate the causal structure for maybe for a period of time, and also you can see in the not causal structure there are indeed some redundant causal structure, the not causal structure, right? But because we propose compact representation, we can see, although it's more likely to nurse some redundant code structure or wrong or incomplete code structure in the dynamics model, but it's easier to optimize the reward relevant code structure, so we can easily to filter some of the wrong or redundant code structure. Also, we cannot see we can fill out all the redundant code structure or yeah, but it indeed solves this problem to some extent.
Mhm.
Yeah.
Absolutely. Thank you.
So that's why we propose the compact representation is to solve this
Right.
problem. Yeah.
Absolutely. And then you showed us how it does outperform it without the
Yeah.
compact representation. Okay, thank you. Okay, so from our Hugging Face audience, for the generative model, the main motivation to use it is to predict the binary masks for the predicted reward calculation. And for the reward, how did we choose the reward states? So I guess the question was, is the main motivation to use it to predict the binary masks for the
Uh, how did we choose a reward state?
Mhm,
Uh, I think this question is related to how we optimize the code structure, right?
mhm.
Maybe let me share my slides. Yeah, I think um the function the loss function can answer this question.
Okay, wait, I can,
Yeah, here.
are you able to share your screen now?
Yeah, can you see the loss terms?
No.
Mm,
I think maybe try and reshare.
oh,
Okay. We can see your desktop.
yeah,
Yes.
here.
Yeah, wonderful.
Um, indeed, our uh, loss functions are similar to the common used loss functions. Here to optimize the causal structure related to the reward, we use this function. You can see we assume the discounted sum of predicted Markov rewards can approximate the long-term return R. And while we predict the reward, the Markov reward, we the reward predictor will take as input the state action and also the causal structure. And to uh, how how do we predict it here? So the RT is the causal structure, uh, multiple ST, and the causal structure from action to reward, multiple the action. So if the reward so the component of state or the action is related to the Markov rewards, the causal structure, the element in the causal structure would be 1, and if not, it would be 0. And so the code structure is optimized with the reward function, and to make it as sparse as possible, we add another regularizer. That's we want the code structure can be as sparse as possible. That we want to remove um, the redundant causal structure, redundant edges to avoid some trivial solutions, like we can make all the code structure equal to 1. Yeah, that's how we optimize the causal structure. And yeah, it's also related to how we select the reward relevant state components. Yeah.
That makes total sense. And again, if there are follow-up questions, feel free to send them in. And we will be happy to keep explaining. Um, okay, we have another Zoom question. So Apart from the medical and healthcare use case, can you kindly further clarify your research applicability for the use of autonomous vehicles?
Uh, yeah, I think it's indeed related to the autonomous vehicles. As example, maybe we safety would be a big problem um, in such a problem. Really, we want some state component or the value of the state would not would be less than a threshold. Like we don't want the vehicle uh, run too fast. Yeah, just an example. So if we know how the state component or the action component can impact the reward or can impact the next state, we can maybe do some constraints on the uh, on each state component. That would be very valuable for such a problem. Yeah.
Thank you. Um, okay, going back to my list here. Um, okay, so kind of going toward the end of your paper, you mentioned some limitations, which include assumptions of a stationary reward function, static causal graphs, and full observability for the agent. So how do these constraints affect the applicability of the GRD framework in kind of like dynamic or partially observable settings? And on that, what potential strategies could address these challenges in future work?
Yeah, it's a really a good question because I think there are two main constraints. The first one is POMDP, like we cannot access all the state space. We can only observe observe some part of the state. Usually we call it a partially observation. But there are many represent representation learning techniques can estimate the state. So it's really easy to extend our method in such a case. And also, and also another limitation is the exceptions. We need like invariant reward structure, dynamics causal structure. Yeah, that's indeed the the exception. But such a exception is widely widely practical or general in the real world because the dynamics of like a vehicle, like the physics of a robot is really keep invariant during the time changes. Yeah, and for those dynamics and time variant structure dynamics models, I think we should. It's indeed available to develop more advanced techniques for such settings. Yeah.
Absolutely. Um, and this question kind of goes right off of that one, but how do you see this work evolving? So I guess kind of like the future directions of making making it more robust to these cases.
Yeah. Just like mentioned before,
Mhm.
yeah, we also work on these directions. Like we want to extend our work into partially observation
Mhm.
frameworks. Yeah,
Yeah. Okay.
and also more advanced causal technique to estimate the causal structure.
Okay.
That would be very valuable.
Absolutely. And just on that, how do you how do you think you would make your estimation techniques more advanced? Like in which specific areas of those estimations?
Um,
And it's okay if you don't know now. I know that's probably a whole other um
I think it's
dissertation.
related to the specific setting and
Yeah.
practical application. So it's
Ah,
hard to see how we develop a
yeah.
very general
Mhm.
method to address all the settings.
Okay, so kind of
So
making it more case specific
yeah,
and really okay for specific applications. Yeah,
yeah,
that's really exciting to hear too, because I know that's kind of a bit of a trend, at least in other parts of machine learning, such as large language models, is tailoring it to specific applications for to outperform general models. So
yeah.
that's a cool connection there. Um, yeah. So I'll invite any last questions from either our audience here on Zoom or on Hugging Face. Um, but if none come in the next few minutes, oh, we have maybe one more. Sorry, I'll just wait. Okay, we might have a few more. But I guess so. For my questions for the paper are kind of up, but Yudi, I wanted to know a little bit about kind of where your research is taking you at the moment. If you have any directions after this paper.
Um, yeah, I indeed follow up this
Mhm,
paper
mhm,
to develop more advanced methods like just mentioned many times. I want to like we can address the partially observation settings, and also because my research interest also lies on LM and multi-agent learning.
mhm.
So there are more challenging setting in such cases. Like for LM, the really we can only get episodic reward because we only know if the task finished after all the answer
Yeah.
we got all the answer. So that's also a case of episodic reward, the delay reward. So
Okay.
I also work on this, and also in multi-agent, this work is focused on single agent part. So
Mhm,
there is only one dimension of maybe create assignment, but
mhm.
in multi-agent, there may be multiple dimensions. Like we not only want to know how team rewards from each time step impact the episodic long-term return. We also want to know how each agent contribute to each team reward,
Right.
the current team reward. Yeah,
Mhm.
I think there are very interesting feature direction after this work, and
Absolutely.
also follow up this research.
Hmm. Totally. That's really interesting. And I think we have one more question from our Hugging Face audience. So, for the confounders in the limitation, is it mainly like adversary and self-play environment? Let me know if that needs more clarification.
Uh, it says means there may some confounders beyond the assumed causal graph.
I think maybe it's referring to yeah, let me know if you can clarify in the audience, but I think it's referring to the limitations we just discussed in terms of, like static uh what was it? Yeah, static graphs, full observability. So um so
Yeah,
yeah.
I think um, is a thing is a sense of acceptance. In this work, we just want to present the idea, so we assume we capture all the uh, like variables in the causal system.
Mhm.
But also, if there are some confounders, we need some advanced technique to estimate the confounder or to estimate the code structure more accurate.
Mhm.
That's also a future or public um, or some directions after this work. Yeah,
Mhm.
so
Absolutely.
also, yeah.
Yeah. And I guess just to extend that to practical settings, what kind of confounders would you encounter in applied settings? I guess just any applied setting. So like healthcare or autonomous
Uh,
vehicles.
in fact, in our environment, maybe there are less confounders
Mhm.
like this, but I know some the wind. Maybe the wind um can can impact the dynamics function and the reward function at the same time. I
Yeah.
think there are some work
Hmm.
uh also focus on this. Yeah.
Yeah, absolutely. Um, well, I'll wrap it up now, but for anyone in the audience with further questions, please reach out and I can forward your questions to Yudi. But I want to thank a huge thank you to Yudi for presenting her work and for Dr. Du for joining the call. And we'll have our next reading group in February, so please sign up if you're interested and please stay connected with us. But yeah, thank you both.
Thank you.
Thanks.